This is an online learning (LMS) project. The task course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Content: M signals in temporal and spectral domain. Tone modulation. M detector/demodulator. Double sideband suppress carrier, DSB South Carolina, modulation. DSB modulators and detectors. Quadrature carrier multiplexing. Single sideband modulation, SSB. Vestigial sideband modulation, VSB. Frequency translation, up converter and down converter. Frequency division multiplexing, FDM, and process. Consider a sinusoidal carrier wave C of t defined by A, C, cosine 2 pi FCDA. C is the carrier amplitude, and FC is the carrier frequency. An amplitude modulated M wave may thus be described in its most general form as a function of time, as follows: S of t is equal to A, C, in parenthesis 1 plus Ka M of t times cosine 2 pi FCD. M of t denotes the baseband signal, that K is the specification of the message. Ka is a constant called the amplitude sensitivity. When Ka times M of t in absolute value is less than 1, we have no phase reversals, so the graph looks something like that. When we have Ka M of t larger than 1 or smaller than -1, we have phase reversals, as shown in the graph. Question: AM process. A carrier signal and a message signal are defined below. Find the expression for the transmitted signal S of t if we use amplitude modulation, AM, for these signals. Also, plot the modulated signal S of t. C of t equals to cosine 2 pi 10 to the 6 t. M of t equals rectangle t over 10 K. A equals 1 over 2. Solution: for better visualization, the modulated signal is also drawn when a cosine wave with 1 Hz frequency is used. Question: AM process 0 crossing. Draw the following signal S 0 crossed t and observe the envelope distortion. Also, propose a modification in the system to overcome this issue. Solution: 1. Of the conditions for transmitted signal S t to have the perfect envelope of the message signal M t is that K A times M t in absolute value is smaller than 1 for all t. In other words, 1 plus K A times M t never crosses 0. If that happens, envelope distortion occurs. It is also called overmodulation. Sin function has the minimum value approximately -0.2 and the maximum value 1. It crosses 0 periodically. When the Ka parameter, namely amplitude sensitivity, is chosen accordingly, 1 plus Ka times M t crosses 0 for some t, and that is where the envelope distortion occurs. ERRL outputs, message signal and time and frequency domain are denoted in the graphs. Note that these are real physical signals generated and observed by electrical instruments. Modulated signals, in a similar manner, look like these. AM signals, temporal and spectral. An arbitrary signal, M of t, is drawn here. Note that it is a randomly drawn message signal and does not necessarily have an explicit form. In frequency domain, a representative signal spectrum is given as M of f. Note that it is drawn representatively, and does not necessarily comply with any explicit mathematical form. Now consider amplitude modulated signal S of t. In time domain its shape is as follows. Taking the frequency domain, it yields the S of f denoted here. Graph representation is as follows. Note that it is a duplicated, scaled and shifted version of the message signal M of t. Question A. M process frequency domain. A carrier signal and a message signal are defined below. Same as the previous problem. For this system, find the expressions for the message signal, carrier wave, and modulated signal and frequency domain. Also, draw them using only positive frequency axis for carrier wave and modulated signal. Example, tone modulation. Examine this example of tone modulation. Message signal M of t is equal to a m cosine 2 pi fmt. Modulated signal S of t is, then, a c times in parenthesis 1 plus mu cosine 2 pi fmt times cosine 2 pi fct, where mu is ka times a m. Consider the maximum and minimum amplitude ratio as follows. A max over a min is a c times 1 plus mu over a c times 1 minus mu. Mu is then equal to a max minus a min over a max plus a min. S of t is rewritten as a c cosine 2 pi fct plus 1/2 mu a c cosine 2 pi fc plus fmt plus 1/2 mu a c cosine 2 pi fc minus fmt. This signal and time domain corresponds to this 6-term frequency domain representation. Question A. M signals, temporal and spectral. A carrier signal and a message signal are defined below. We use amplitude modulation. Find the expression for the transmitted signal S, t. Find its frequency domain representation, S, F, and draw it. Draw only the positive frequency axis. C of t equals cosine 2 pi 10 to the 6 t. M of t equals rectangle t over 10 k. A equals 1. Solution. We use only the positive frequency axis, but keep in mind that, in theory, there is also the negative frequency components, which is symmetrical to the positive ones. Power analysis of a m signal, a m tone modulated signal S, t, can be explicitly written in 3 terms: the carrier, the upper side frequency, and the lower side frequency. In the single tone modulation scheme, carrier power is 1/2 a c square, and upper and lower side frequency powers are equal to 1/8 times mu square a c square. Graph shows the power usage with respect to modulation percentage, that is varying mu. M is power inefficient. There is carrier power plus 2 side bands. M is bandwidth inefficient. There are 2 side bands. Question: percentage modulation, bandwidth. Consider the message signal, M of f, below. Find its first null bandwidth. This message signal is amplitude modulated with a carrier wave of cosine 2 pi 1000 t. Find the modulated signal bandwidth and compare it with the message signal bandwidth. Solution: you can find the message signal bandwidth visually by finding the first null on the graph of M of f. Passband bandwidth is twice the baseband bandwidth for amplitude modulation. Question: percentage modulation, power. Consider the message signal, M of f, below. This message signal is amplitude modulated with a carrier wave of cosine 2 pi 1000 t. Find the power allocated for the sidebands and carrier component of the modulated signal S of f. Compare them, and if possible find an absolute ratio between sideband powers and total power. Assume modulation factor mu equals 1. Solution. Look at the course book, Communication Systems, Haken, Moher, pages 77 and 78, to see how the power is allocated between the sidebands and carrier component. As a general rule, the sideband power to total power ratio is mu square over 2 plus mu square, where mu is less than 1, as a rule of thumb, to avoid overmodulation. Therefore, in the best case, the sideband power, that is essentially the message content, is only 1/3 of the total power of the signal transmitted. Efficiency. Here is a block diagram of modulator. As we have discussed already, it is wasteful of both power and bandwidth. Alternatives are double sideband suppressed carrier modulation, DSP South Carolina; vestigial sideband modulation, VSB; single sideband modulation, SSB; envelope detector, receiver. Block diagram of envelope detector of waves. Received signal is something like that, and envelope detection yields this. Question. Envelope detector, receiver. Find the load resistance and capacitor values for an envelope detector with 3 MHz carrier frequency and 1 kHz message signal bandwidth, and 30 MHz carrier frequency and 1 kHz message bandwidth. Pick your resistor and capacitor values from the table provided. Solution. The product R times C must be very large than 1 over Fc, and at the same time much smaller than 1 over bandwidth. Double sideband suppressed carrier, DSP South Carolina, MESCA signal M of T. It is limited by some bandwidth W, and this modulation scheme, S of T, is equal to C of T times M of T, where C of T is a C cosine 2 pi Fc T. Compare it to standard M and see that there is no carrier, in other words peak, transmitted. So it is more efficient. Also bear in mind that a peak in frequency domain corresponds to a cosine of some sort, and hence it is a deterministic signal. There is no need to transmit a deterministic signal and waste bandwidth and power for it. All sources, as much as possible, should be allocated for the message signal itself, in some form. Question. Double sideband suppressed carrier. A carrier signal and a message signal are defined below. We use double sideband suppressed carrier modulation. Find the expression for the transmitted signal ST. Find its frequency domain representation, S, F, and draw it. Draw only the positive frequency axis. C of T equals cosine 2 pi 10 to the 6 T. M of T equals rectangle T over 10. Solution. As you can see, in contrast to standard AM, we suppress the carrier, so we gain from the power. Question. AM block diagram. In the diagram below, a typical AM system is given with its input parameters. Find the output in time and frequency domain. Solution. First, write down the operation the block does. It consists of a mixer and a summer. After writing down the expression of the block, you will see that it is the typical expression for an amplitude modulator. Balanced modulator, used to AM modulators to be arranged in a balanced configuration to cancel out the carrier. Take the AM modulator, use it in this configuration to cancel out the carrier. Balanced modulator, generating the DSP-SC signal example. In this slide, we go over the block diagrams in detail to show the process of generating a double sideband suppressed carrier signal from the traditional AM signal. This configuration is also known as balanced modulator. At the input of the system, we feed a linear combination of message signal XT to the traditional AM modulators. This configuration is set up so that the carrier is cancelled out at the summer. So, at the end we have the DSB signal as message signal times the carrier, unlike traditional AM, which has the additional plus carrier term. DSB detection, coherent detection. This block diagram shows a DSB coherent detector. After signal reception, the signal S of t is multiplied in time domain with the locally generated signal A prime C cosine 2 pi fct plus phi. This results in the intermediate signal V of t. Passing V of t through a low-pass filter gives 1/2 A prime C times A C cosine phi m of t, so you get your message signal in some explicit form. DSB detection, coherent detection. Example: after generating S DSB and sending it through a channel, now we shall see the demodulation process in this scheme. Unlike AM, simple envelope detection 1D work. Instead we have a more complex demodulation system, consisting of a product modulator and a low-pass filter. Let S DSB denote the received signal with no channel effect on it. The signal is multiplied by a sinusoidal wave C prime t generated at the local oscillator of receiver. Ideally, we would want C prime to be equal to Ct of the transmitter, but because no two oscillators can be identical, there will be a frequency and phase offset. For simplicity, let us only consider a phase offset phi. After the product modulation, we have two terms at the output, Vt, a high-frequency term at double the carrier the frequency, and a baseband term. Baseband term is the message signal times some other constants. To retrieve the message signal at the baseband, we low-pass the Vt and get V0 of t, which is equal to 1/2 times cos phi times message signal. On ideal conditions, phi would be 0, and we would get the message signal at its maximum power, phi equals pi/2, and minus pi/2 are ill-conditioned offsets, which result in 0 received power. Question: DSB detection, coherent detection. For the detection of the signal given below, S of t, find the appropriate local oscillator and low-pass filter parameters. Namely, find f, c, of oscillator and magnitude spectrum of h, of f. Use the smallest possible bandwidth for h, of f, s, t, equals rectangle t over 10 cosine 2 pi 10 to the power 6 t. Solution: use the first null bandwidth of the message signal to get to the lowest possible bandwidth of the low-pass filter h, of f. Quadrature carrier multiplexing. It is possible to generate and send two independent message signals at once using this method. See that S of t resulting from this operation is equal to A C m1 of t times cosine 2 pi fc t plus A C m2 of t times sine 2 pi fc t. Two terms in this summation are orthogonal to each other, one being in phase and the other is quadrature. Multiplexed signal S of t can be decoded at the receiver side as follows. Question: quadrature carrier multiplexing. For quadrature carrier multiplexing, two message signals are given as M1 equals rectangle t over 0.1, M2 equals sinc 10 t. Find the expression for S of t and its Fourier transform S of f. Carrier frequency is 1 kHz. Single sideband SSB modulation. Single sideband modulation can be done by filtering out one side of the DSB modulated signal. This is DSB. Using filtering, one side is rejected along with the carrier. Single sideband SSB modulation audio signal. Following is how an audio signal can be transformed from DSB to SSB. SSB voice signal. SSB finds its greatest application in the transmission of an analog voice signal. Analog voice has very little energy at low frequencies. This results in an energy gap shown in the figure. It is easy to construct an SSB modulation scheme with the spectra of message signal. Question: SSB voice signal. Assuming after the DSB modulation, we have the following transmitted signal spectrum. Find the correct filter response H of F to transform the DSB signal into SSB. Pick either side, lower or upper sideband. Finally, draw the SSB signal spectrum. Solution: note that voice signals in baseband start from a low frequency but not zero, and end at some intermediate frequency level. This sort of signal spectrum is effectively suitable for SSB modulation because one sideband is separated from the other by a reasonable gap. SSB transmission system, two-stage. SSB transmission in two stages is done as shown in this block diagram. SSB transmitter, two-stage modulator, HF radio. SSB transmitter with two stages is denoted here with the depiction of the signal spectra at some stages. Excellent monolithic filters available at 9 MHz, so the implementation of this block diagram is quite handy. Vestigial sideband modulation, VSB, TX. Vestigial sideband signal is generated by passing the double sideband signal through some filter. The response of the filter H of F is like this. It includes one side and some residual part, hence the name vestigial. The resulting signal S of F is A, C, over 2, M of F minus FC plus M of F plus FC, times H of F. Practical application of SSB to a signal, having no zero gap around the origin, requires some part of the other band, a vestige of the other band to be passed. Vestigial sideband modulation is used in TV signals in USA, for example. VSB, TV signals, M plus FM, analog TV signal and frequency domain has a spectra, as this. The filter function H of F has the spectra, as shown. This is a VSB modulated digital TV signal. Why VSB? Detection is easy. Envelope detector. Significant low frequency content. Large bandwidth. Digital TV signal spectrum. Here is a digital TV spectrum in VSB modulation format. Frequency translation, up/down conversion. SSB is open to frequency changing/translation, mixing, or heterodyning. Diagram shows how to change only the frequency of a signal S of t. The diagram does this: S1 of t multiplied by L cosine 2 pi FLT, which yields M of t cosine 2 pi FLT plus A L cosine 2 pi FLT, which is then written as 1/2 A L M of t times, in parenthesis, cosine 2 pi F1 plus FLT plus cosine 2 pi F1 minus FLT. The signal then passed through a bandpass filter to filter out the unwanted frequency component and get the desired one, that is one of the cosines. Question: frequency translation, up and down conversion. At the receiver side of a communication system, a high-frequency signal, center frequency of 8 GHz, is needed to be down-converted so that it can be processed. The bandpass filter after the down-conversion has a frequency response figure depicted below. Find the down-converter frequency value. Satellite transponder. Block diagram of a satellite transponder system. This is actually an up and down converter. Different frequency bands are used in satellite communications. Therefore, there needs to be different frequency signals at hand. Frequency division multiplexing, FDM. This diagram shows a compact frequency division multiplexing system. This whole diagram uses ideas we know from previous slides. Question: Frequency division multiplexing, FDM. 3 message signals are defined as below. M1 T equals rectangle T over 0.01. M2 T equals sync 80 T. M3 T equals triangle T over 0.1. These signals are multiplexed by frequency division multiplexing. The lowest carrier frequency is 1 kHz. Guard band is 100 Hz. Find and sketch the spectrum of X, B, of F. Solution. Keep in mind that, in this scheme, we are using single sideband modulation, so the spectrum will be shaped accordingly.